Hi, welcome. In this video, we're going to talk about persistence and I/O devices and hard disks and disk scheduling. So let's get started. All right, so what is persistent data? That is data that survives a power loss. What does that mean? It means when you turn off your computer, the persistent data is on your disks, whatever type of storage devices that you're storing it, and it will still be there the next time that you turn on your computer. So the two main jobs of a computer are to do input and output, or I/O, get the data, and process the data. The responsibilities of the operating system is to manage your devices and provide different services. Some of the services that are provided are buffering, caching, spooling, scheduling, scheduling not only for the CPU, but scheduling for your devices and handling errors. In addition, the devices could have device drivers which assist the operating system and abstract the devices. So that managing I/O is a very big part of the operating system. You have all of this data and all of these different devices that vary in the way that they are connected, and they vary in the way that they work. And so there's a lot of changes, and they're changing all the time and trying to get faster and work more efficient and store more data. So it's very important for the operating system to be able to uh, work with these devices and work efficiently and utilize the resources as the best way possible. So you have different types of buses on your system. You have your memory bus for your CPU and your memory, you have your I/O bus, and you have your peripheral bus. Some of the different ways that the operating system is going to communicate with these devices and the data. The first one is polling. Polling is not as efficient as interrupts. Polling is checking, like busy waiting. You keep checking and checking to see when things are ready. Sometimes that's really necessary, especially if it's something critical. And, keep in mind that devices are not the same speed as have all different speeds. So sometimes you want to check to see if something is ready. Most modern operating systems are more interrupt driven. Another way to get data from memory to devices is called direct memory access, which is transfers data without the CPU, but you need a DMA controller to do that. There are different types of interrupts, like we've said before, that most modern operating systems are interrupt driven. So you can, if you're waiting for some data, you can go and do something else, and then you get an interrupt to let you know when that data is ready. There are two types of interrupts. One is maskable. That means that you can disable that interrupt, and the other one is not maskable for critical data. You cannot disable that interrupt. So let's go a little bit over communication. Like I said before, the polling technique, you actively check the status of the device, and it's like busy waiting, so you're taking CPU cycles to do this. The interrupt technique, you just wait, and when the device is ready, you get an interrupt, and you have an interrupt handler that's ready to deal with that. And I just said the difference between maskable and non-maskable interrupts. All right, so the functions of the kernel I/O subsystem is to control access, to manage your files and devices and directories and all of that. Buffering, so buffering, because there's varying speeds of devices, then the data needs to be stored somewhere. So your operating system will have a buffer where it's stored because there's different speeds. But one thing about a buffer is that the buffer may store the only copy of the data. So depending on how that where the buffer is, and the operating system has to make sure that this data gets transferred. The second thing is caching. So caching stores fast copies of data, and the key word here is copies. So could be cache coherence problems where you have to make sure that you have the most up-to-date copy of the data. Spooling is queuing output for like a slower device, for example, like a printer. You have schedulers for your devices, the same possibly the same way that you're going to schedule your processor. Obviously, your processor works a lot more, so that's why we studied and did more examples of CPU scheduling, but you do also need to deal with scheduling devices and recovering from errors. So some operating systems try to be very fair with the scheduling. So we're not studying any scheduling algorithms for devices. We spent a lot of time on scheduling for the CPU, and here we just know that sometimes there are devices, per queue, per device queues for different data. And then the operating system will have to put stuff in a buffer because the varying speeds between your devices, and sometimes there's going to be double buffering, and then you could have those problems where you don't have the most updated copies of data if you have more than one copy. So we already talked about caching and spooling. All right, so this is just an overview. You have your device driver that, you have different controllers and different devices that are connected, so they have their own drivers, and that hides some of the differences to make, if you think about when you're using your computer, everything, whatever computer you're on, whatever operating system you're on, there's a fluidity to the way that the operating system makes everything appear as if it's all part of the same system, but you have many different types of devices that work in different ways. So devices can vary in the way that the data is stored and transferred. You could have character or block, stream data or block data, sequential data or randomly access the data. It could be synchronous or asynchronous, different speeds of operation, and data could be read, write, read only, or write only. So this is just different ways that you're going to get the data from the devices and combinations of these, and this all has to be handled to make it all uniform for the operating system works to make it all uniform. So we talked a little bit, actually we've talked quite a bit this semester about swap space management. This would be the medium-term scheduler. Sometimes in memory you have to remove things from memory, but they're still active, so you put them somewhere in your disk and you have to store that. So the operating system, many operating systems offer this swapper or swap space management where you're not using up your memory for things that are, maybe you run out of RAM, or you're using your memory for things that are not currently active, so you can put them swap it out somewhere on the hard disk, usually some type of a partition on your disk for this data to temporarily store it, and then it can be swapped back in. This we called it the medium-term scheduler or the swapper back when we were talking about scheduling. So direct memory access requires a DMA controller. This is where you just bypass the CPU to transfer between devices and memory. How does the operating system handle errors? Well, usually you're going to have some type of, well, there's two things. You have error codes, and then you also have logs. Your system is always logging all kinds of things that are happening. And, this is overhead. The operating system, when you have to deal with something, the operating system has to stop what it's doing and log this and use the resources in the computer this is a part of the management system to log and create reports, and then there's different techniques once that's done. Sometimes it's sent to, you can see where sometimes it'll pop up and say, oh, we're going to send this out to the to the manufacturer or whatever, so that they can possibly deal with this situation, or you're just going to have to recover from that error, start again. So different things have to happen, but the key point here is that the operating system needs to be able to handle errors that happen. So the different types of storage, I know that nowadays a lot of modern computers use solid state disks or SSDs. These do not have moving parts, but disk drives, hard disk drives are still used. They do have moving parts, so we're going to spend the rest of this module discussing hard disk drives and different ways to search on a hard disk drive. Optical drives are slow, like CDs and regular disks. So let's get started and talk about the hard disk. So the hard disk drives all of the data is presented as a big array of logical blocks. So let's look at the structure of a hard disk. You have a bunch of platters, and on those platters, they are concentric tracks. All of the tracks on all of the platters are called a cylinder. And then the tracks are broken up into little pieces called sectors. So the top view like this. So a cylinder would be, so the track are this, these are tracks. All of these circles like that are the tracks. Actually, maybe I could, yeah. So this would be a track, and then a track, etc. So those are tracks. When you take all the tracks together, that's called a cylinder. And within the tracks are broken up into little sections, and those are called sectors. So the one point here, you can notice that there's going to be a lot more data on the outside than there is going to be on the inside. And that comes into play when we're talking about different algorithms like C-scan and C-look algorithms. Okay, so sector 0 is the outermost sector, or track 0. So the outermost cylinder would be 0, and like I said before, you can notice when you look at this that there's way more data on the outermost track than there is in the inner tracks. So the operating system works with controllers to minimize the seek time. So when you have data that's on a cylinder, then you want to go get the next data. You're going to there's algorithms that can be used to decide. Also, it's a mechanical thing, so you don't want to be moving more than you have to. But then there's also so seek time is the distance to the cylinder. We're going to be using cylinders when we go over these exercises. And also there's also, you have to take into consideration the transfer of the data and all of that, because we're just talking about algorithms that move to the right cylinder, but then there's also a latency when the data gets transferred. So the different disk scheduling algorithms are first come, first serve, shortest seek time first, the scan algorithm, the look algorithm, the C-scan, and the C-look. So let's just kind of go over how this works. This is the queue. So this queue right here means the cylinders. So the head is currently at cylinder 53, which is right here. And if you're doing first come, first serve, you're just going to move along from 53 to 98 to 183 to 37 to 122 to 14 to 124 to 65 and 67. You can see, a hard disk is mechanical, so you can see that this is a lot of back and forth movement. So not only is it going to be a lot of movement, like if you added up all the total head is 650 cylinders, but it's also a lot of back and forth. So this is not going to be the most efficient way to get your data and go to the correct cylinder on your disk. The next one is going to be shortest seek time first. So you are wherever you start at 53, and then you're going to go through the current list of requests and go to the closest one. This requires this could cause some starvation. Number one, it also requires the overhead of calculating which is the closest one, but it will have less movement. So you go to 65, then 67, then 37, then 14, then 98, 122, 124, then over to 183. So the total head movement is going to be a lot less. However, this is going to be, it's going to have overhead of calculating the where to go next. Then there's the scan algorithm. This is sometimes called the elevator algorithm, and this just goes back and forth in either direction. So if you were to do this, if I gave you this exercise and I said you start at 53, you need to know where your previous position was because you need to know which direction to go in. This scans in both directions. It just keeps going all the way across and scanning in both directions. And so if any more requests come in the queue, it'll hit it if it comes along the way or get it on the way back. So here we're at 53, so we know that our previous position was greater than 53. So I'd have to give you that information, so we just scan along. The other thing about scan is it's going to go all the way to the end, and then turn around and get all the requests all the way to the end, and then it would turn around again and just keep going back and forth. That's why it's sometimes called the elevator algorithm, and you need to know the previous position to know which direction it's going. Look is the same thing. The only difference with look is it doesn't go all the way to the end, so it's just going to go to the farthest one, which is 14. This is 14, and then turn around and go back, go to 183, and then turn around and go back, and you also need to know the previous position for this one. C-scan, this has to do with, like I said before, the outermost cylinder has more information. So this is going to jump to the outermost cylinder. So it only services in this direction. In other words, it only services from the outside to the inside, then jumps to the outside, then services towards the inside, then jumps to the outside. So obviously it's going to have more total head movement, but the jump is not going to be transferring in any data. It's just a smooth jump back to the outside. So here we go. This is the outside. If you remember the disk, the outside is 0. So this would be track 0. And if you have the platters all together, then that would be cylinder 0. And then this would be, so in this case, if we have 200, that's 0, then this would be 199 in the middle. So C-scan is going to service requests in this direction. So any requests along the way, and then it's going to jump back out and then service more requests in that direction. So it does the jump. So you can see that C-scan goes also all the way to the end. And C-look is the same idea, only it doesn't go all the way to the end. It only goes at that, so it has that little bit of calculation to make sure that there's no other cylinders in the queue that are greater than 183. Then it'll jumps to 14, and then it starts servicing again in that direction. All right, so how do you select which disk? How does the operating system select which disk scheduling algorithm? There's a lot of things that go into this choice. So shortest seek time first is common, but there's always going to be drawbacks. If you choose something, it has, shortest seek time first obviously is going to get you to the closest cylinder, but you have to calculate and constantly look at the queue that's coming in, which one is the closest. So sometimes it might just be better just to go back and forth with the scan or a C-scan. Or a look, but again, the look also requires calculation, but it doesn't waste any time going all the way to the end. Thank you.